Here is a second example of heat energy and calculating using the formula from the previous video on specific heat capacity of Q equals mc delta T, or some textbooks will write it Q equals ms delta T. The C and S are often used interchangeably for specific heat capacity. Okay, so let's start in with this problem. Now hopefully you have watched the previous video on specific heat capacity energy calculations to get an introduction to this formula, how to manipulate the values and so forth. This is a little more complicated, a little bit more challenging of a problem. But again, we're going to use that same system of, as we read a problem, we're going to write down the values, the quantities that are given, label them, and then we can do some substitutions into our formula and solve for the unknown variable. Okay, so if 980 kilojoules of energy, 980 kilojoules of energy, and that is a Q value. That is, when I see joules or kilojoules, I know that I'm referencing a Q value, an energy value. So 980 kilojoules of energy are added to 6.2 liters of water. Okay, so 6.2 liters, that is a volume measurement. Okay, and it is of water. Okay, so I'm going to write that down because we know that our specific heat capacities are dependent upon the material. We have to find those specific values. Okay, now the water is starting at 291 Kelvin. So that is an initial temperature, a starting temperature. Okay, so that 980 kilojoules of energy was added to the 6.2 liters of water while the water was at 291 degrees Kelvin. All right. Now, the question is, what will be the final temperature? So what is TF? Okay. All right. So this is what we are given. This is our formula. Now, we know our substance here is water. Now, we can go and we can find the specific heat capacity for water from our textbook. Now, in every chemistry textbook, there should be, in the chapter where we're studying, there should be a data table that has specific heat capacities of some common substances used in the example and end of chapter problems. So I'll go look in that book, in the textbook, and look for water, and this is liquid version of water. So it is a 4.18. Now, please do not forget the units. Okay, the data table will have them, joules per gram Kelvin. Okay, so 4.18 joules per gram Kelvin. Okay, so we've got all of our values now. So let's substitute in what we have. Okay, we've got a Q, 980 kilojoules. Now, let's pause there. Look at the specific heat capacity that I retrieved from our data table in our textbook. Notice that's joules. This is kilojoules. Okay? This is like apples and oranges. These are different units, so I need to get these in the same scale. Okay? So I'm going to change this 980 kilojoules to 980,000 joules. Remember that 1 kilojoule is 1,000 joules. Same as 1 kilogram is 1,000 grams. Okay, so we've got our 980,000 joules. That's our Q value. Our mass, oh, they didn't give us a mass. They gave us a volume. Okay? Now, you're far into the chemistry course, so hopefully by now you've been introduced to density. And you know that the density of water, okay, this is liquid stage, is 1.0 grams per milliliter. Okay, grams per milliliter. Alright, we have 6.2 liters. Well, we know that 1 liter is equal to 1,000 milliliters. So we can determine then that 6.2 liters, okay, 6.2 liters, and 1 liter has 1,000 milliliters, and the density is 1 milliliter has a mass of 1.0 grams. Okay. See, this problem's a little bit more challenging because we're having to do some conversion units, but it's very doable. Never give up on these problems. Write down what you have and then retrieve prior knowledge. Chemistry builds on itself. So liters cancel, milliliters cancel, leaves us with grams. So 6.2 times 1,000 times 1 gives us 6,200 grams. Okay, and that is a mass value. So we'll put that right here. 6,200 grams. Again, remember to put your units. The specific heat capacity, we retrieved it from a data table in our textbook. 4.18 joules per gram Kelvin. Okay, so grams and grams, that's common. Joules and joules, that's common, so we're doing well. Now we need our delta T. But we don't have a change in temperature, we just have an initial temperature. But we do know from the previous video and from the textbook examples that the change in temperature, the delta T, is equal to the final temperature minus the initial temperature. Final minus initial. So we have here final minus 291 Kelvin. Okay, so this right here is equal to delta T. That's what we have so far. So we can't solve for delta T. You know, we don't know what our final is. We don't know. So we're kind of at a block here, but that's okay. Okay, so let's solve this. Okay, so I'm going to leave delta T in this equation, because then I don't have to do as much distribution. So I'm going to, here on my calculator, do 6,200 times 4.18, and I'm going to get 25,916. I'm going to take that and then have delta T, so I will have those two. Okay, see, I combine these two terms. I'm leaving this as delta T because I only know half of. I only know the TI, not the TF. So, and my units, what would be my units? Well, grams would cancel, and I would be left with joules per Kelvin here, multiplied by delta T, and that's all equal to this 980,000 joules. Now, let's divide both sides by the 25,916. That will leave us with delta T, a change in temperature, and so many degrees Kelvin. So we have 980,000. Okay, 980,000 divided by 25,916, and we get 37.8. And as you can see, it's a very continuous long decimal, but we are going to round for 3 significant figures. No, we need to go all the way back to 2 significant figures with this 6.2 liters. So we're going to take our 37.814 continuous and on, and we're going to make it 38 degrees Kelvin. Now, 38 degrees Kelvin is our change in temperature. What is change in temperature equal to? That is final temperature minus the initial temperature. Our initial temperature was 291 Kelvin. So now we have 38 Kelvin is equal to final temperature minus 291. So we can isolate, and we have a final temperature equal to, we bring this across, 38 plus 291. So we have a 9, and we have a 2 and a 3. So 329 Kelvin is what we have here. 329 Kelvin is our final temperature.